There are monsters out there, lurking in the dark. For centuries, astronomers scanned the heavens again and again without ever spying them. But behind the familiar stars and nearby calm galaxies of our universe lay something far more vicious, far more terrible, and far more powerful. Completely invisible to the human eye, you would never see them even on the darkest of nights. Indeed, at first, they appeared as nothing but dim, distant pinpricks of strange radio emission. But those pinpricks revealed something no astronomer could ever have expected. Something so strange, so bizarre, that for years nobody even believed that they could exist, that there must have been some mistake in our observations. Thankfully, none are nearby, for if they were any closer, they would flood us, our galaxy, our solar system, our planet, with deadly radiation. A single one of these monsters can easily pump out over 10 to the power of 40 joules every second. For comparison, our sun outputs about 10 to the power of 34 joules, 1,000,000 times less, every year. The brightest among them outshine stars, outshine galaxies, outshine 1,000 galaxies at once. Some extreme events, like the most powerful supernovae, can briefly become brighter than these beacons. But those events are temporary, ephemeral, flaring and dimming in a matter of weeks. When these monsters awaken, they stay powered for millions of years. In just a fraction of their lifetime, they can easily produce more energy than even the most intense cosmic explosions. And they are hungry. They feed on anything and are capable of tearing apart entire stars in a single fit of rage, producing flashes of radiation and jets of charged particles that shoot out for millions of light years, piercing through galaxies and spreading their destruction throughout entire clusters. They are the Quasars, the most powerful engines in the known universe. But what drives these engines? What powers these lighthouses in the deep? The answer will take us on a journey through some of the most extreme physics in the universe, and even provide us with a grim warning. For though our galaxy is quiet now, it will not stay that way forever. The most distant quasar from us is 13 billion light-years away. It would take nearly the entire history of the universe to travel to, and that's without the universe expanding at the same time. Space is big and getting bigger, and sometimes that can make us feel small. BetterHelp is our sponsor today. They are the world's largest therapy service and are 100% online. BetterHelp can match you to one of over 30,000 therapists in their network based on your needs, preferences, and location, giving you access to a wider range of expertise than may be available in your area of the universe. You can schedule therapy sessions at a time that's convenient for you, and if you feel like your therapist isn't a great fit, you can switch therapists with a click of a button in your settings at no additional cost. With BetterHelp, you get the same professionalism and quality you expect from in-office therapy, but with a therapist who is custom-picked for you, with more scheduling flexibility and at a more affordable price. So, get 10% off your first month at betterhelp.com/HOTU, and I've also linked them below in the description. Thanks to BetterHelp for supporting educational content on YouTube. At first, astronomers had no idea what they were seeing. By the 1950s, science had grown used to the idea of galaxies outside the Milky Way, but even in this expanded cosmological view, the belief was that the universe was relatively small, only a few billion light-years across at most, and that expanded cosmos seemed relatively simple, even boring. There were galaxies, there were clusters of galaxies, there were vast expanses of nothingness. For a time, astronomers were able to convince themselves that they were finally starting to figure things out. But in the mid-20th century, there was a technological revolution. Optical telescopes, capable of seeing objects in visible wavelengths of light, were becoming enormous. And our ability to use the rest of the electromagnetic spectrum, wavelengths of light outside the visible, grew along with that. And with these new observations came the realization that the universe was far weirder than we could have ever imagined. One of the first revolutions was in radio. In the 1930s, the pioneering engineer Karl Jansky solved the problem of how to reduce noise in sensitive radio antenna and discovered the first radio signals coming from deep space. Among many bright and obvious sources like Jupiter, the Crab Nebula, and nearby galaxies, astronomers also discovered numerous, small, faint, distant, point-like radio objects. These strange objects appeared all over the sky, emitted radio waves at a broad range of wavelengths, and could not be seen with visible or infrared telescopes. The only clue they gave was their position. They appeared both within the band of the Milky Way and outside of it. Since our galaxy is a thin disk, this meant that the sources either had to be extremely close, like the visible stars of the night sky, or extremely far away, like the distant galaxies. But if they were close, we should have been able to see them in optical wavelengths, and if they were extremely far away, their intensity in radio wavelengths implied they were the brightest objects in the entire universe. Understandably, many astronomers pushed back against this interpretation, not only arguing about their distance, but also openly questioning what could possibly power something that bright. Finally, a breakthrough came in 1962. By the 1960s, astronomers had been able to refine the techniques of radio astronomy to the point they could more precisely measure the location on the sky of these strange sources. With these new techniques, astronomers Cyril Hazard and John Bolton found that one radio source, known as 3C273, would undergo occultations of the Moon, allowing them to provide an extremely accurate estimate of its position. Following up on that work, the Dutch-American astronomer Martin Schmidt discovered a faint object in the same location, in the visible spectrum. Within that visible light, Schmidt found the usual collection of bright spectral lines and dark gaps, the fingerprints of elements and molecules found throughout the cosmos. But these lines were not in their usual wavelengths. Instead, they were shifted towards the red end of the spectrum by nearly 16%. To get that kind of redshifting, either 3C273 had to be moving away from us at an incredibly fast speed, or it had to be incredibly far away. By this time, astronomers had been slowly accepting the Big Bang theory of the universe, the view that the cosmos was once smaller in the past and is continuing to grow in the present day. Under cosmological expansion, light from distant objects redshifts because the space between them and us expands, stretching the light out into longer wavelengths. And when he interpreted the redshifting of the light from 3C273, Schmidt realized it sat 3.4 billion light-years away. It was the most distant object, by an order of magnitude, ever observed. In 1966, Time magazine put Martin Schmidt on its cover, comparing the magnitude of his discovery to those of Galileo, saying, "The 17th century Italian startled scientists and theologians alike. The 20th century Dutchman has had an equally jarring effect on his own contemporaries." 3C273 was a revelation. It is so distant that it appears to us as simply a point-like object of incredible luminosity, in fact making it another record breaker. It was also the brightest known object in astronomy at the time. Stranger still, 3C273 was remarkably compact. Now knowing the location of the object, astronomers dug back through archival photographic plates and found that earlier generations of astronomers had already seen it, without recognizing it for what it was. Year after year, 3C273 had shown up, but its brightness had varied between annual observations. To change brightness within a year, an object must be smaller than a light-year across, because any changes to the object can only propagate at a speed lower than the speed of light. So not only was 3C273 far brighter and far more distant than any known object, it managed to accomplish both these feats in a volume smaller than our solar system. With this technique of matching radio sources to visible light objects in place, astronomers went on to confirm the distances to dozens of these so-called quasi-stellar radio sources, the name coming about as early astronomers knew that these objects were not normal stars, but had absolutely no clue what they actually could be. It was in 1964 that the astrophysicist Hong-Yi Chu coined its modern, catchier name in the journal Physics Today. So far, the clumsily long name quasi-stellar radio sources is used to describe these objects. For convenience, the abbreviated form, quasar, will be used throughout this paper. And so, the quasar was born. Debate over the true nature of quasars raged for decades within the astronomical community. Many astronomers believed that the original interpretation was correct, that these were incredibly bright, incredibly compact, and incredibly distant objects. But they could not explain what powered these extreme objects. Others continued to argue that these were some sort of exotic star, much closer to our own galaxy, that provided such an extreme amount of gravitational pull that light escaping from them would redshift, making them appear much more distant than they really were. But it wasn't one decisive measurement that cemented the cosmological nature of quasars, but rather a gradual build-up of observational pressure, which grew hand in hand with the acceptance of the Big Bang. The Big Bang theory tells us that the universe changes with time. Not only was it smaller in the past, it was also different. Quasars only appear in the extremely distant universe. Indeed, the nearest quasar sits over 700 million light-years away. Since astronomy acts like a time machine, with more distant observations revealing the nature of a younger universe, these observations tell us that quasars were only active in the distant past and have now gone quiet. This idea fits perfectly with the Big Bang, because we expect the universe to change as it evolves with time. Our dawning understanding of the age and size of the universe helped paint a portrait of a gigantic, ancient cosmos that could easily accommodate the distances to even the most far-flung quasar. And so, astronomers were left with little choice. They had to accept that these strange, intense objects were truly far away and truly bizarrely bright. As news of the discovery of quasars worked its way from purely astronomical circles and into the popular imagination, public interest skyrocketed, with writers using the term to elicit a sense of strangeness and remoteness. And if you need a new nursery rhyme to soothe your child, you can take the words of legendary physicist George Gamow. Twinkle, twinkle, quasi-star, biggest puzzle from afar. How unlike the other ones, brighter than a billion suns. Twinkle, twinkle, quasi-star, how I wonder what you are. Meanwhile, astronomers discovered more and more quasars, including ones that were both unusually bright and oddly dim. The very brightest ones got a new name, blazars, while others weren't emitting any radio waves at all, but were somehow extremely bright in X-ray radiation. And as radio astronomy became more sophisticated, astronomers were able to capture smaller, finer details. The most famous example was Cygnus A, one of the brightest radio objects in the entire sky. Initially thought to be an exotic radio star when it was first discovered, by the 1950s astronomers realized it was far stranger. The central core of Cygnus A was a galaxy, but extending hundreds of thousands of light-years away from that core were two thin, long jets, ending in gigantic bubbles, screaming in radio emission. All of these strange objects, whether loud or quiet in the radio, whether relatively nearby or extremely distant, shared one thing in common. Their cores were abnormally bright. In some cases, the nuclei of the galaxies outshone all the hundreds of billions of stars within the galaxies themselves. The brightest of these cores indicated an enormous amount of activity, of unknown origin. Without knowing the true explanation, astronomers conceived of a brand new term to encompass them all: active galactic nuclei. And so what was going on in the cores of these galaxies? Why were some the most luminous objects in the universe while others were relatively quiet? What generated the radio emissions, and why did some blast out X-ray radiation? Astronomers had discovered a zoo of active galaxies throughout the cosmos, with a dizzying and confusing array of galactic creatures. Something must power them. Something must generate the energies needed to make the brightest of them outshine 1,000 galaxies at once. Something must enable them to be seen from the distant reaches of the far universe. These active galactic nuclei must have something in common, and it was clear that that something lived in their cores. And so to understand what drives these, the most powerful engines in the known universe, we have to look a little closer to home. "25,000 light-years away sits a monster. We wouldn't know it by looking at it. We can't see this monster with our own eyes. We can't see it with telescopes. But even decades ago, we knew that something strange was there. When we look out at the sky on a dark, clear night, we can see the band of the Milky Way. The Milky Way is brightest in the direction of the constellation Sagittarius, and it's there that astronomers discovered the core of our galaxy. And when radio astronomers began their first, hesitant explorations of the sky, they also found a bright source of radio emission coming from this point. Later astronomers, building a catalogue of radio sources, ranked the brightest object in each constellation in alphabetical order, and so the bright source in Sagittarius became known as Sagittarius A. Still later, more detailed observations revealed an exceptionally bright, point-like object buried within the larger Sagittarius A complex. Because the discovery was exciting, and excited states and atoms get labelled with an asterisk, the modern name for the object at the very centre of the Milky Way was born: Sagittarius A star. It was the same problem posed by the distant quasars, but much closer to home. What could possibly power the bright radio emissions coming from the centre of our galaxy? And so they pushed deeper into the maelstrom, and deep within the core of Sagittarius A star, astronomers found stars. Pinpricks of light dancing and swirling. Repeated observations showed that the stars were orbiting around some unseen companion, bound by chains of gravity to something massive and something dark. Simple calculations of orbital mechanics revealed the mass of the central object, forcing scientists to acknowledge the existence of an entity weighing over 4 million solar masses. Debates swirled for decades, but eventually only one plausible answer remained. Sagittarius A star was a supermassive black hole. Black holes are common throughout the universe, most the leftover remnant of a massive star. These black holes are usually relatively small, weighing only a few times the mass of the Sun. But the mysterious object at the centre of our galaxy weighed millions of times the mass. How could such a giant black hole form, and how could it find itself at the centre of our galaxy? In 2022, all debate on its identity was put to rest when the Event Horizon Telescope unveiled their stunning image of Sagittarius A star. Using a network of telescopes spanning the entire globe, the Event Horizon Telescope team spent years carefully combining and correlating their data. The result was a blurry, low-resolution image of the true nightmare sitting within our galaxy's heart. A fuzzy ring of superheated plasma swirls around an evacuated core of pure blackness. At the very center lies the black hole itself, its event horizon preventing any background light from traveling through it. But the immense mass of the supermassive black hole distorts gravity to such a degree that light behind the black hole can instead curve up and around the event horizon, giving us a view behind the monster. The black hole itself appears larger than it really is, again due to the extreme warping of space-time. Lines of sight that would normally graze past the edge of the event horizon instead wrap around it. From our perspective, the globe of the black hole unfolds itself, revealing every angle of it in a single image, producing what's known as the shadow. That extreme gravity, capable of bending and distorting light like a funhouse mirror, reaches out to the surroundings of the black hole. Stars that whip too close to the event horizon risk their doom. If they pass within a critical distance, the gravitational forces tear the star apart in a process called a tidal disruption event. Most of the gas, however, settles into a distant orbit around the black hole. But 25,000 light-years worth of gas and dust sit between us and the center of our galaxy. That gas and dust scatters and absorbs most wavelengths of light, preventing us from seeing the Sagittarius A complex directly. Indeed, if we could, it would be one of the brightest objects in the sky. Radio waves, however, pass through the interstellar medium relatively unaffected, which is why we only saw the first hints of trouble when we turned our radio observatories towards that constellation. But despite the fearsome radiation pouring out of the gas surrounding it, the black hole itself was relatively quiet. It was nothing like the distant quasars with their luminosities millions of times higher. Indeed, except for a faint smudge of radio emission from outside our galaxy, you wouldn't even know that a supermassive black hole was there. But still, the question was asked, could these be related? Could black holes power the quasars? If our galaxy hosted a supermassive black hole, perhaps others did too. As cosmologists began to understand the Big Bang theory more fully, they realized that structures in the universe had to grow slowly. Long ago, there were only small differences in density across the cosmos, with hardly any variations. But over the course of hundreds of millions of years, those density differences grew. At large, cosmological scales, the only force that really matters is gravity. A patch of matter with a slightly higher density will attract its neighbors, pulling more matter onto it. That will give it an even stronger gravitational pull, which will in turn pull even more matter towards it, and so on, in a never-ended feedback loop that drives small structures to become big ones, leading eventually to the first stars, clusters, and galaxies. All this gravitational action leads to incredibly high densities in the cores of these structures. It's simply where matter piles up the most. The cores of galaxies host many stars, and those stars are much more massive than average. They live short lives and quickly die, becoming black holes. And packed into such small volumes, the black holes quickly merge together, their sizes growing out of control, becoming supermassive. The idea that black holes could power quasars was first proposed in 1964, just a year after the identification of the first quasar itself. But most astronomers rejected the idea outright. After all, at the time, black holes were considered a wild and probably unphysical hypothesis. Einstein's general relativity was certainly a radical reshaping of our understanding of gravity, but that didn't mean that every corner of its mathematical structures had to be replicated in the universe. The concept that matter could compress so tightly that no other force could withstand it was outlandish. Surely some process would stop a dead star from catastrophically collapsing into a point of infinite density. But then astronomers came across an intriguing system, known today as Cygnus X1, a bright source of X-ray radiation in the constellation Cygnus the Swan. Astronomers spent years trying to understand how this star could produce so many X-rays, until observations later in 1972 by astronomers Louise Webster, Paul Murdin, and Charles Thomas Bolton revealed that it was not one star, but two. The X-rays came not from the invisible companion itself, but from the swirling plasma surrounding it. Detailed observations of that plasma allowed astronomers to calculate the mass, and more importantly, the density of that companion. Whatever it was more compact than any known star, and more compact than any star possibly could be. Famed astrophysicist Stephen Hawking even bet against the possibility of Cygnus X1 containing a black hole, saying in his book, A Brief History of Time, that, when we made the bet in 1975, we were 80% certain that Cygnus X1 was a black hole. By now, 1988, I would say that we are about 95% certain. But the bet has yet to be settled. 10 years later, he finally conceded defeat. Cygnus X1 was the first confirmed black hole. With black holes known to exist, everything clicked into place. The universe readily created stellar mass black holes. These black holes could merge and consume material, swelling them to epic proportions, and these giants would find themselves in the centers of most, if not all, galaxies. And so observations confirmed that everywhere we looked, every galaxy hosted a supermassive black hole. We couldn't see them, they were, and continue to be, too far away to allow us to monitor their orbiting stars directly. And for all the sophistication of the Event Horizon Telescope, besides our own Sagittarius A star, it has only managed to capture an image of one other galactic core. But astronomers could use the brightness of the quasars themselves as a way to measure the mass of their central black holes. If supermassive black holes did power quasars, then they could use Doppler shifting to estimate the black hole's mass. But for this to work, the black holes had to somehow power the quasars. How could they do that if black holes are purely gravitational? How could something that only pulls on the surrounding matter produce such fearsome energies? The red klaxons blare, and a moment later you feel your ship shuddering, jolting uncontrollably. The stresses on the hull are almost too much, threatening their integrity. Together with the alerts flashing on your display comes a new, ominous warning chime. A flood of cosmic rays have struck the ship, microscopic particles slipping through the molecular structures and straight into the hearts of the crew. But you are determined to go on. You push your ship forward, allowing it to slip into the swirl of plasma in a relativistic frenzy. You don't even bother trying to control it anymore, as the forces here are so strong, so far beyond known physics that there's no choice but to give in to their mercy. The ship is in uncontrolled freefall. A quick glance at a side readout reveals what you already suspected. The external temperature is reaching millions of degrees, with the internal life support systems beginning to fail. Gripping the armrest, you can do nothing but watch as system after system fails. Frustrated, you swipe away the warnings. There's nothing new they can tell you. After yet another final lurch, one strong enough to throw you against your restraints to the point of bruising, comes a sudden relief. Silence. You bring up the warnings. They're clear. The temperature outside has plummeted to nearly absolute zero. The cosmic rays have vanished, the radiation subsided. Your ship is still in free fall, but stabilized, no longer tumbling. You activate the external cameras. Shielding retracts, revealing the optics, sending their feed directly to your display. And there, dead ahead, you see it. Or rather you don't. The reason you launched this mission to the center of the galaxy in the first place. The black hole. The deep hearts within the cores of galaxies are complicated, busy places, like city centers. There are far more stars than average, compressed into uncomfortably small volumes, like city dwellers crammed into tiny apartments, street after street. There are also far more aging red giants located here, a testament to the ability of the cores of galaxies to produce greater numbers of the most massive stars. But within all this brightness and intensity is a dark side. Astronomers estimate that the core of our own galaxy hosts tens of thousands of smaller black holes, a retinue in service to their master at the center. Countless supernova detonations, gravitational tidal interactions and more tear stars apart, their tattered remains scattered among the close-packed stars. Nothing much lasts long in the intensity of the core. And among all that chaos sits a thick ring of cold dust, a choking ring of smog within the central city. It is wide, around 1,000 light-years thick, and the dust slowly circles around the center. It's also as thick as it is wide, forming a gigantic torus, and is so cold that the molecules and dust within it are neutral. If you were to travel through it, you would hardly notice it due to its low density, but that dusty torus obscures our view of most galactic cores, as it efficiently absorbs most of the radiation coming from within. Only when we look from above or below do we get a direct view of the maelstrom. While calm and non-violent itself, that ring of dust signals an important transition point in the galaxy. Outside the ring, you are in the galactic environment, the suburbs, the physics dominated by all the gravitational and electromagnetic forces of the galaxy at large. But within the ring, only one thing matters: the supermassive black hole. It is the central landmark to guide all lost travelers. While even the largest ones take up less than 1% of the total galactic mass, they are by far the most massive singular objects within a galaxy. Far enough away from them, like our own solar system is, away from Sagittarius A star, we don't feel or even notice the black hole. But within the torus of dust, the gravity of the black hole takes over. Within this region, the black hole's gravity dictates the motion of every star, every clump of gas, and every speck of dust. It's here that some stars stray dangerously close, their orbital motions bringing their speeds up to a few % of the speed of light. If they get too close, they're torn to shreds, their atoms joining the trains of gas on their dreadful march towards the event horizon. Even closer to the black hole, that gas begins to lose control. Unable to dictate its own motion, it gets lost in the crowded frenzy, funneling to incredible speeds, driven by the extreme gravitational environment. It is this process that releases an incredible amount of energy from the simple act of falling. And to get an estimate of the amount of energy released, we look at something called the binding energy. To understand binding energy, imagine wanting to move a pile of stones sitting at the bottom of a valley. To move the pile, you must grab each individual stone and bring it to the top of the ridge. Every time you do this, you just overcame the gravitational potential energy of the stone. You can estimate how much energy you'll need for the entire task by calculating the potential energy of all the stones. Now imagine pulling these stones from the bottom of the valley and sending them so far out into space that they never come back. Now repeat that for every single atom of the Earth, effectively destroying the entire Earth in the process. The amount of energy you would need to obliterate our planet is called the binding energy. For a black hole, imagine dragging a particle from the event horizon all the way out to a distance of a few thousand light-years, fighting against the gravity of the black hole the entire time. That is the binding energy of the particle around the black hole, which is equal to the energy released when the particle falls from that distant orbit into the event horizon. And for a typical supermassive black hole, that energy is roughly equal to the rest mass energy of the matter itself. This process isn't perfect, and not all the energy available is released as the particle falls. Usually only about 10% of the binding energy converts into other forms. That may not seem like a lot, but compare that efficiency to the 0.1% of the rest mass energy released by thermonuclear reactions in the hearts of stars. But this process doesn't lead to an uncontrolled release of energy like a bomb. Instead, the release is slower and in stages, a steady build-up of excitement as material continues to cram towards the black hole. As the gas heats up, it emits radiation. Normally, radiation only makes things warm, but the intensity here is so high that the radiation has a pressure. It is so intense that it can push on things. Imagine the summer sun so strong it literally could knock you over. The radiation pushes the gas, heating it up even more and sending it away from the black hole. But with the gas pushed away, it can't continue accreting, and so the radiation dissipates. But eventually the gas cools down again, allowing it to condense towards the black hole and repeat the accretion process. This cycle of collapse and inflation acts like the piston in a car engine, keeping the flow of gas in check, preventing it from suddenly crashing into the black hole all at once, and keeping quasars shining for millions of years. Yet that is just the beginning, for the gravity around supermassive black holes does not work alone. As any surrounding gas funnels towards the black hole, its orbital speed increases by simple conservation of angular momentum. An ice skater can pull their arms closer to their body to increase their rotation speed, and so can material speed up as it whirls closer to the black hole. But eventually, its inward movement is slowed, the rotation supported by centripetal acceleration, like a planet locked in orbit around a star. And so soon enough, the loose collection of orbiting gas and dust compresses into a tight, thin disk of accretion around the supermassive black hole. All that infalling and compression heats the gas to incredible temperatures, the gravitational potential energy surrounding the black hole converted into heat, friction, and radiation, a simple matter of too much material cramming into too small of a volume. The disk glows, primarily at ultraviolet wavelength, but also across a broad range of the electromagnetic spectrum. In addition, the disk constantly streams out showers of high-energy particles known as cosmic rays, electrons and protons accelerated to nearly the speed of light. Those microscopic bullets can occasionally strike a wandering low-energy photon at infrared or visible wavelengths. And when that happens, the particles transfer their energy to the photons, turning them into high-energy X-rays. The intense heat of the disk causes the cold atoms and molecules to unbind themselves, forming an electrically charged plasma, the same state of matter as lightning. These rapidly moving electric charges around the black hole create a magnetic field, and very quickly it generates the conditions needed to power a dynamo, a seemingly infinite supply of energy that can turn a small magnetic field into something devastating. Initially, within the disk, the magnetic field lines follow the motion of the gas, swirling in rapid circles around the black hole. But the innermost regions of the disk rotate far faster than the outer regions, forcing the magnetic field lines to coil up on themselves, storing up a tremendous amount of energy. The motion of the gas within the disk isn't smooth and steady. Instead, it's chaotic and turbulent, like a running river, with portions of gas clumping and colliding, waving back and forth as they swirl in the firestorm. When a clump of this gas drifts away from the disk, it pulls on the magnetic field like a bit of string. But the difference in rotation from one section of the disk to another twists that loop of the magnetic field around itself. The action of rotation eventually stretches that magnetic field back down into the disk. This is a dynamo at work, which turns chaotic, turbulent motions in the disk into an increasingly strong magnetic field surrounding the black hole. Normally, magnetic fields don't affect the motions of matter, except in very small ways. But as the magnetic forces ratchet up within the accretion disk surrounding the giant black hole, they begin to dominate the motions of material. The closer the gas gets to the black hole, the more unstable the orbits become, and there is a certain special distance known as the innermost stable circular orbit. Any gas that falls below that orbit is doomed. Most of the gas falling towards the black hole ends its life at the event horizon, never to be seen again. But some gets caught in the twisting and winding paths of the magnetic field lines. Their force is so strong that they channel and guide the gas as it falls. But how does this lead to the radar pinpricks we see in the distant sky? That is still a bit of a mystery. One hypothesis is called the Blandford-Znacek process, named after the two physicists who came up with the idea. The key to this idea is the fact that the black hole itself is rotating. When it does, it drags space-time in the region around it, like moving a heavy coffee table twists the rug beneath. This region, called the ergosphere, forces any object entering into it to rotate along with the black hole. This includes magnetic fields. The strong magnetic fields within the disk punch in and out of the ergosphere, which forces them to twist up on themselves. Twisting fields create a tube of magnetic energy stretching above and below the black hole. While most of the charged particles following those magnetic field lines end up plunging below the event horizon, some just barely scratch the surface, accelerated by the extreme magnetic energies within the ergosphere. Following the lead of the field lines, the charged particles race away from the black hole in the form of long, thin jets of radiation, lighthouse beams racing out into the dark. This radiation is primarily composed of radio waves, and it is here that we finally find the origins of quasars. The particles in the jets are incredibly powerful, accelerating to nearly the speed of light. They race out of the galactic core and punch through the galaxy altogether, stretching for up to millions of light years. Eventually, however, they lose steam, the particles interacting with the intergalactic medium that surrounds every galaxy. When they finally stop, they create a high-pressure zone of charged particles. These bubbles transfer heat all the way from the innermost regions surrounding the supermassive black holes into the volumes of entire clusters of galaxies, which can stretch for over 1 million light-years across. That is how powerful these systems are. Not only can they be seen from across the cosmos, but they can raise the average temperature of entire galaxy clusters, the largest gravitationally bound objects in the universe. This picture, involving supermassive black holes, the ring of dust surrounding them, the ferocious accretion disk, and the magnetized outflows, explains almost every observation of active galaxies. If we see the central core of a galaxy face on, we see the intense radiation from the accretion disk combined with the strong radio emission from the jet, and we recognize it as a quasar. If we happen to be looking directly down the barrel of the jet, then we get the most extreme emission, and we call it a blazar. It's like humanity first encountering cats in astronomical observations. Sometimes they see the whiskers, or a paw, or a swishing tail. Initially, these seem like completely different objects, but over time, we realize that they're really just different perspectives of the same kind of creature. But what of other active galaxies that aren't even allowed in the radio spectrum? The solution here is that not every galactic core is active. To power a quasar, the black hole needs to feed. Without a supply of new material, the entire system shuts down. No gravitational collapse, no accretion disk, no twisting magnetic fields, no relativistic jets, no nothing. This picture also explains why we see no quasars in the nearby universe. Active galactic nuclei can last for incredibly long times. The longest-running quasars can run for over 1 million years, but they require constant streams of new material to feed their fires. The early universe was much smaller than it is today, with galaxies much closer together and undergoing frequent mergers. With every merger, new material finds its way to the center of the galaxy, setting off a feeding event, a new round of quasar activity. But today, with the universe much older and far larger, galaxy mergers do not happen often. With no new supplies of gas, we see no quasars in the local volume of the cosmos. Indeed, our own galactic core is quiet. Although Sagittarius A star hosts stars, dust and gas around it, it's a relatively empty region compared to the cores of quasars. But this was not always the case. In 2010, astronomers using the Fermi Gamma-Ray Space Telescope identified 2 gigantic regions stretching above and below the galactic plane, each one over 50,000 light-years across. Computer simulations revealed what caused them: a feeding event several million years ago. Whether it was a cluster of stars or a wandering clump of interstellar gas that met its end in the hungry maw of Sagittarius A star, our black hole destroyed it quickly, shredding it into an accretion disk around the event horizon. And then the same physics went to work. The accretion disk energized a powerful magnetic field, which created jets and launched relativistic particles away from the galaxy, where they still sit today. Indeed, it seems that every galaxy has gone through at least one active phase, spending some of its life cycle as a quasar, with the central core of the galaxy, barely a few light-years across, outshining not just its own galaxies, but 1,000 galaxies combined. But despite our growing comprehension of the incredibly energetic forces powering these vast dynamos, the quasars we see are still too bright. The supermassive black holes that serve as their gravitational power sources are also very, very big. Too big. And they are not the only issues. Astronomers continue to discover quasars appearing in the earlier and earlier universe. Too early. Quasars seem impossibly big and impossibly bright, existing impossibly early in the history of the cosmos. What does this mean? Everything about quasars is the very definition of extreme. The largest known supermassive black hole weighs over 66 billion solar masses. If you were to place that black hole in our own solar system, with its singularity at the center, by the time you reach the orbit of Pluto, you would be less than 1% of the way to its event horizon. We currently know of around 1 million active quasars, and suspect that there are at least 10 million more in the observable universe yet to be seen, each one pumping out more energy than 1,000 galaxies combined, each one a fierce engine of plasma and radiation. And quasars have been with the universe almost since its birth. The most distant known quasar, named J0313-1806, was firing when our universe was only 670 million years old. That's just 5% of its present age. But astrophysicists aren't quite sure how these black holes appeared so early and got so big in the relatively short age of the cosmos. The only way that we know for sure how to make black holes is through the deaths of massive stars, so by this logic, the first black holes couldn't exist until the first generation of stars lived and died. If those early stars were like the stars of the modern universe, then they left behind black holes no more than a few times the mass of the Sun. From there, the black holes had to grow, and they have two options available: merging and accreting matter. Black holes, especially massive ones, don't merge all that often, at least theoretically. Initially, when two black holes encounter one another, interactions with their environments allow them to draw closer together. But eventually, all that's left between them is their own gravitational pull. As the black holes wind around each other, they emit gravitational waves, which pulls energy out of the system and allows the black holes to sneak closer together. Once the black holes are within a few light-years of each other, sufficient gravitational wave emission alone would take longer than the age of the universe. And astronomers still don't have a solution to this obstruction, calling it the final parsec problem. Yet despite this, we do know they merge. For we have detected signature ripples in space-time from merger events with gravitational wave detectors. And when we scan the cosmos for supermassive black holes, we usually find only one residing in each galactic core, despite each galaxy having suffered multiple merger events. So although the universe has clearly solved the final parsec problem, we don't yet know how. However, even the most optimistic estimates for black hole production and merger rates can't explain the largest and earliest quasars. So that leaves accretion to give black holes their exceptional masses. But once again, we run into a problem. The same seesawing of radiation and gravitational collapse that keeps quasars illuminated for millions of years prevents large amounts of gas from reaching the black hole quickly. This process is known as the Eddington limit, and while not a hard and fast rule of the universe, it does present a challenge. If black holes are to reach supermassive status, they need to find a clever way around this, and somehow shove extra material through the event horizon without heating it up to the point that it escapes the vicinity of the black hole. Compounding this problem is the lack of observational evidence for so-called intermediate mass black holes. These black holes should sit in a mass range well above stellar mass black holes, which weigh only up to a few dozen times the mass of the Sun, and below supermassive black holes, which weigh millions or billions of solar masses. We should see these in-between class black holes everywhere, representing an intermediate stage of growth between the stellar mass and supermassive black holes. But we don't. On the other hand, the results from gravitational wave detectors suggest that black holes are emerging far more often than we had initially assumed. In order to get the detection rates that we observe, many small black holes had to have merged in the history of the universe, meaning that they find each other, close their orbits, and merge quite efficiently. In addition, those same results suggest that there are many more small black holes than we had initially assumed based on simple stellar deaths. The result is a confusing, tangled mess. It is clear our understanding of the growth and evolution of black holes is missing something. Traditional models of galaxy and star formation don't seem to be cutting it, so perhaps it's time to turn to more exotic models. One possibility is that dark matter itself can directly collapse to form black holes. Dark matter is the dominant form of matter in the universe, making up roughly 80% of the mass of every single galaxy. But in the simplest models of dark matter, it doesn't interact with itself, and so has difficulty clumping together at small scales. When it comes to something like a galaxy, most theorists assume that the dark matter is roughly evenly spread out. But in some more complicated models of this mysterious form of matter, it is capable of small, infrequent interactions with itself. This would cause it to clump together rapidly, especially in the high-density days of the early universe. And if enough dark matter clumps into a small enough volume quickly enough, then its own gravitational weight can take over, leading to catastrophic collapse and the formation of a giant black hole. A black hole potentially big enough to begin powering quasars before the first stars had even arisen. Another possibility is that our assumptions about star formation don't apply in the early universe. In today's cosmos, stars can only get so large. This is because the nebulae that collapse to form them can only grow to a certain size before they begin to efficiently lose their heat and collapse. But that efficient cooling depends on the presence of heavier elements to radiate away the energy of the nebula. The early universe, however, lacked such heavier elements, because massive stars have to live and die to enrich the interstellar medium. So perhaps stars hundreds of times more massive than the Sun could have formed. When those giant stars die, they would leave behind much larger black holes. Or perhaps the solution is something even more exotic. Maybe black holes have been with us since the earliest moments of the Big Bang. In this scenario, the exotic conditions and phase transitions of the first few seconds in the history of the universe spawned countless small black holes, known as primordial black holes. Though many observations have ruled out the existence of black holes like these, there is still the possibility of their existence. There may not be a lot of them, but if enough survived into the age of galaxy formation, they could provide a shortcut to quasar building, bypassing the usual route of star and black hole formation. It's these questions and many more that provided motivation to build the James Webb Space Telescope, which is currently probing the first generations of stars, galaxies, and quasars to appear in the universe. Regardless of these mysteries, one thing has become clear. Galaxies and their supermassive black holes are inextricably linked together, and the formation of quasars plays a key role in that relationship. And in the early 2000s, astronomers made a startling realization. It's not just simply a matter of every known galaxy hosting a supermassive black hole at its center, but the properties of that black hole are closely linked to the properties of the host galaxy. For example, the greater the black hole mass, the higher the temperature in the galactic core and the higher the stellar velocity within. And the larger the black hole is, the more massive the overall galaxy is. and so it appears that supermassive black holes don't evolve independently of their host galaxies, and turning on and off quasar activity plays a key role in that self-regulating connection. If a galaxy accretes a lot of material, either by gravitationally attracting gas in its surroundings or by cannibalizing another galaxy, that galaxy now has a lot of new material to boost star formation. But a lot of that material winds its way into the core, which turns into an accretion disk and launches a jet, turning the core of the galaxy into a quasar. All that radiation envelops the black hole's host galaxy, heating the entire contents of its interstellar medium. If the gas is too hot, stars can't form efficiently. This means that what would have been a burst of sudden star formation turns into a steady trickle. But this is good for the galaxy. Too much star formation at once would use up all the available reservoirs of gas, which would ultimately end star formation too soon. But the quasar acts like a brake, preventing too many stars from forming in a short period of time. It seems almost every galaxy has gone through a quasar phase, and these galaxies continue to regularly pump out new stars at a predictable, efficient rate. This quasar back and forth explains the relationship between galaxies and their supermassive black holes. When the galaxy grows larger, so does the black hole, and feedback from the quasar keeps star formation in check. And this also applies to our own galaxy. The Milky Way grew from countless mergers and cannibalizations of smaller galaxies, and each one of these interactions could have flooded the galaxy with so much new material that star formation became uncontrolled, using up all the available gas in just a few 100 million years. But Sagittarius A star kept us in check, preventing stars from forming too quickly. Indeed, it could be that without Sagittarius A star activating as a quasar deep in our distant past, then our own sun may never have formed, and we may never have been here. But this happy equilibrium will not last long. In 5 billion years, our galaxy will begin to merge with our nearest neighbor, the Andromeda Galaxy. Our two supermassive black holes will find each other and also merge. Material, tattered remnants of stars and nebulae destroyed by the gravitational forces of the merger will find its way into the new core. And when it does, the slumbering giant in the center will reawaken, activating its mighty engines of gravity and magnetic fields and pouring its tirelessly fierce radiation into the new galaxy, snuffing out any hopes of peace and quiet for ages to come. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.